Geotechnical earthquake engineering deals with behavior of soil and foundation under earthquake loading. Unlike the static, earthquake load are dynamic and cyclic, which create huge destruction as you can see in this all earthquake depicted all together. In 2001 Bhuj earthquake, it was very dangerous earthquake. In 2015 like Kashmir earthquake, Indo-Nepal earthquake and Taiwan earthquake. These are the recent earthquakes. While in 1964 Niigata earthquake, another El Centro earthquake, Loma Prieta earthquake and New Zealand earthquake. All these major example of earthquake which creates the disaster and death of people and loss of the lifeline. So why the earthquake happens? Suddenly release of huge energy due to which ground shakes and everything is in start in the motion. Now, what is the objective? To assess the seismic hazard at site due to source, evaluate the soil response of the ground shaking, design the safe foundation and earth structures, reduce the earthquake induced ground failures. What are the engineering application? So seismic design of buildings, bridges, dams, tunnels, roads, power plants, foundation of all the structures, urban planning in earthquake prone areas. These are the some example of earthquake like Indian Ocean tsunami, which creates very devastating uh, damage to all the countries in the Indian Ocean. And this is one example where you can see the destruction happen in Turkey, where everything get collapsed during the earthquakes. Why the structure get collapsed? Structure get collapsed due to the strong shaking. Like when the earthquake is having low magnitude, it hardly damage the structure. Of the moderate shaking will create some corner cracking into the building, and some strong shaking will damage entirely the structure. So this is how we can mitigate such kind of damages by making the base isolators and damper at the top. So this is how Myanmar earthquake creates a damage and destruction and collapse of a newly constructed structure. As you can see, this devastating thing happened due to the earthquake. So that's why study of earthquake is very important. So why the ground fails? The ground fails, this is another type of failure in ground due to the earthquake. The first we have seen the collapse of the structures, and now the ground will fail. So how it will fail? As you can see, one man is a man just dancing on the soil, but the soil is behaving like liquid, so this is called liquefaction. Now you can see this phenomena, liquefaction, during the earthquake. And why does this happen? If it is happening, it will create the ground failure. While you can see the entire soil on the river bank or anywhere on the crust will get cracked and damaged. So let's see what happened into the liquefaction. While the seismic or shaking, while seismic shaking or movement, the soil particle get rotate, revolve, and it just gets displaced from its position. While the contact between all soil particle get removed, and this condition is known as liquefaction. Why the liquefaction happen? When the three-phased soil system experience the earthquake, the effective stresses between the soil particle which happen due to the contact point of the soil just get displaced, and the sudden pore pressure get induced. Now you can see in this photograph, and at that point the effective stress is zero, and the soil will behave like liquid because no contact point between the soil particles. So this is called liquefaction. So liquefact, why stuff sinks? Now you can see in this animation, You can see when the saturated soil, the voids are filled with water. When we stand on it, we can stand properly because the soil particle having contact point with each other which transmit the load of weight. Consider a house standing on the saturated sand and suddenly earthquake hits. What will happen? Everything will vibrate, the water will come up, pore pressure will get increase and building will get collapse. So this is dry soil can sustain higher load while saturated vibrating sand can get liquefy under the load. So this phenomena creates settlement in uneven settlement, differential settlement into the soil where the foundation can collapse and sink. So this is how the liquefaction destroy the structures, roads and any other lifeline, pipeline or the underground tanks. Now we will see what is dynamic property of the soil. So there are two parameters which are very important in soil dynamics, that is shear modulus and damping ratio. So what is shear modulus? Shear modulus is a measure of soil's resistance to shear deformation. And what is damping? Damping means when we apply any load to soil, it thus energy get absorbed, that is called damping. And the ratio is, it is a dimensionless quantity and ability of soil dissipate the energy during the cyclic and dynamic loading such as earthquake or machine vibrations. So this is one example of shear modulus, how the shear stress and shear modulus are get into the picture, and one soil model with damping dashboard. Now you can see in this chart with a higher shear modulus at very low strain, very small strain, the soil will behave elastic in nature, the deformation will be elastic, while the strain get increase from very small to the medium strain. So the strength of the soil get decreases, right, and the degradation will start. So this part we call it the stress strain curve, non-linear and heterosis, where the energy get absorbed. After that, if the stresses are getting increased, if the strain is getting larger, so in the larger strain which comes into the foundation, so the degradation of the modulus happens and sudden drop in the shear strength or shear modulus has been observed here. For engineers, what value plays important? So the first is the Gmax and secant modulus. Why the secant modulus important? Because it is very difficult to calculate the Gmax, but we have the correlation with the shear wave velocity. We can calculate the Gmax. What we should use? We should use the secant modulus, which is lower value than the Gmax. So shear modulus. As you can see, shear modulus denoted by G, it represents the stiffness of soil at very small rate into the soil dynamics in study of earthquake, and where the vibration comes, we usually go for shear modulus at the strain level of 10 to the power minus 4%, which shows the elastic behavior. The shear modulus reaches the maximum value called maximum shear modulus. At this strain level, no permanent deformation we can observe. So you can see in this graph, as we applying the load, soil will deform and it will regain its original position, and it happened at very small strain rate. What is maximum shear modulus? Gmax is equal to rho vs square, where the density multiplied by shear wave velocity square is called maximum shear modulus. So what happened when the strain get increased? Some absorption of the energy takes place, while this is called damping. When the energy is very large, damping will get higher and permanent deformation we can observe in the sand or soil. Now you can see the hysteresis loop. The leaf life structure is called hysteresis loop. When we start loading on the x-axis, there is a shear strain. On the y-axis, there is a shear modulus or shear strength. So when we apply the load, soil get deformed like this, we unload it and again we'll reload it. So while this process, what happened, sort of some amount of energy get dissipated, which is depicted in this blue shaded portion. And this curve line is called backline curve. So tangent to the backline curve is called G max, while we can plot G from this slope. So what happened here, we will see one graph. When the G max, we are having the maximum shear modulus. At the time, the strain will be very low. As the strain get increases, shear modulus get decreases, right? And what happened to the damping ratio? At very low strain, damping is negligible, approximately is equal to 0. While increasing the damping ratio, the strain get higher. So this represents the damping is inversely proportional to shear modulus. Next, we will see dynamic property of soil, how to calculate it. So basically, in the industry, the very important and renowned test, we call it SPT, standard penetration test. The n value has all the correlation with modulus stiffness at dynamic and static state. While ECPT, it is very important test which gives us continuous profile of soil, and it gives the representation of pore pressure as well as its stiffnesses. So these two tests usually perform on any site before the construction, before the design of the soil. Apart from it, if we have to calculate the dynamic property, actual dynamic property, the important test is called downhole test. We can perform it, we can get the value of Vs and Vp, or we can do the CHST, cross-hole sonic test. So we can get suspension logging and we can get the Vs and Vp. After it, we can perform surface wave. We can measure the surface wave velocities also, but these are suitable for the shallower depth. But the cross-hole and DHT, we can perform it for greater depths. Dynamic properties of soil. So SPT will give us soil sample, stratification, grain size, shear strength parameter, modulus parameter, consolidation parameter, but not dynamic parameter. We can analyze the liquefaction, we can calculate the SPC, and we can calculate the settlement. So this is widely used in the industry, while we can correlate this dynamic property, dynamic modulus parameter, based on the n value. Next, to calculate the dynamic property, another recommendation is CHST and DH, cross-hole sonic logger test and downhole test. Yes, we can get the stratification, we can calculate modulus based on Vs and Vp. It is very suitable for the dynamic modulus properties. We can analyze the liquefaction based on VSVP, but we cannot calculate the SBC. We can analyze the settlement based on the stiffness of the soil. So this table shows a lot more tests which happen on the site, like SPT, ECPT, CHSTDH, plate load test, trial pit, CBR, ERT. So these all 7 tests generally perform on the site to assess it for the dynamic state, earthquake state, or for the static state.